Recently, there has been quite some noise around this photo of Blackpool in the Flat Earth supporters and debunkers community. Ranty, who was one of the prominent Flat Earth YouTubers, came back to the Globe site after analyzing it. He presented his analysis on a stream with Baldy Cats and Ruhiv, and debated Brian's logic about it recently. Ruhiv did a separate brilliant analysis as well. Many people are currently talking about this photo, and I would like to add my 2 cents. I've actually already posted a short video about it, but it was very brief, and I decided that a more detailed presentation would be nice. I'm going to be using my atmospheric refraction simulator. It can generate simulated panoramas based on digital elevation data by simulating the propagation of light through the atmosphere over a globe or a flat Earth. I'll describe exactly what it does and how in a separate video. For now, if you're interested and familiar with programming, you can check its source code. It's freely available on GitHub. I'll put a link in the description. The simulator is intended to be used by people other than myself as well. Unfortunately, it's not the most user-friendly piece of software at the moment, so I intend to make another separate video serving as a tutorial. For now, if you wish to use it and are having trouble, you can ping me for help in the comments or find me on Discord. I'll put contact info in the description. Any questions regarding the source code are also welcome. Back to the photo. I will actually show you 2 photos, the famous one taken by Kevin Jackson and another one taken by Bev Try Thinking as an independent confirmation that the view from Kevin Jackson's photo is actually the usual view and not a special case. Hashtag thanks Bev, by the way. In order to create good simulations, I needed precise positions of the photographers. I knew which parking they took the photos from, it was this one in Southport. Then, by looking at the azimuths to some landmarks and some trial and error, I arrived at the positions you can see now. So, Kevin Jackson's position I got agrees with the one Ruhiv showed in one of his analyses, so I have good confidence in it. Regarding the Bev's position, I haven't seen anyone pinpoint yet so far, but if someone has accurate data in this regard, maybe Bev himself, I'll gladly learn how close I am to the correct position. So let's see what the results are. Now, important note beforehand, the simulator is capable of simulating the views both with refraction taken into account and purely geometrically, so as if light traveled in perfectly straight lines. I will show you the views without refraction first, then with refraction, so you can see what kind of a difference it makes. Let's see what the view on the globe should be without refraction. I've already aligned the simulation with the photo, so that Blackpool landmarks like the Blackpool Tower and the Ice Blast in the Blackpool theme park fit nicely. So we can see that if I increase the opacity, they are indeed aligned well, but the mountains in the simulation are clearly much lower than the ones in the photo. So it's clear that in reality we can see more than just pure geometry would dictate. Let's see how about flat geometry. I've used the tower and ice blast for alignment again, and if I increase opacity this time, we can see that with flat Earth the mountains in the simulation are the inverse of the globe simulation. They are much higher in the simulation than they are in the photo. So it looks like neither model fits if we ignore refraction. Let's add refraction then. For a proper simulation, I'd have to know the exact atmospheric conditions on the day the photo was taken, specifically the vertical temperature profile. There is a website providing such data for some locations, and it's this one I'm presenting right now, but none of the locations are close enough to Blackpool. If you look at the UK, it's not really densely populated with the stations. So as far as I know, the real data is unavailable, but if anyone knows a source I could use, please tell me. That would actually be awesome. With the actual conditions being unknown, I have to make a guess. The simplest one is just to use so-called standard atmosphere, which is just the approximate average state of the atmosphere. In this approximation, the temperature gradient at altitudes between 0 and 11 kilometers is assumed to be minus 0.0065 degrees Celsius per meter. It's quite possible that the actual conditions were different when the photo was taken, but it's unlikely that they differed by much. The temperature value is also important. As this was taken in the winter, I assumed the temperature slightly above freezing, 4 degrees Celsius or 277 Kelvin in this case. After plugging all of this into the simulator, what we get is this. An almost perfect fit of all the features in the image. Relative positions of the buildings and the mountains are very much correct. The simulation seems to match the reality almost to the pixel. But there is actually more. Sleeping Warrior spotted one not quite obvious feature in the photo, which he nicknamed the Toothpick. He identified it as a turbine from a wind farm near Ulverston. There are 5 turbines there in total, and we can see them in the simulation. Let me just pop up the simulation. We can see them in the simulation as the cyan cylinders. And one of them actually does indeed overlap with the Toothpick. It's this one. If we decrease the opacity, we can see that this cylinder is exactly where the Toothpick is in the photo. Okay, but how about the other 4 turbines? We can see that the rightmost turbine is where the city buildings are in the photo, so it's reasonable to assume that it's just obscured by the city. Now, if we look at the middle one here, let me zoom in a bit. If we decrease the opacity of the simulation, we can see that in the photo there is a dark smudge here. So it's quite possible that this actually is a shadow or something on a part of the turbine. So it seems that the globe model actually predicted something about the photo that we didn't know beforehand. And as for the 2 leftmost turbines, it's really hard to tell. They are predicted in places in the photo that are really affected by JPEG compression. If you squint, you can see something brighter here and here. So basically where the turbines are supposed to be, here there is a vertical whiter strip, and here maybe there is something, but yeah, it's really hard to tell. So I wrote a message to the author of the photo asking if he could share a less compressed version of this region, but I got no response so far. Anyway, we'll see whether the turbines are there later in the video. We've seen that the globe model fits nicely, but let's check the flat one for completeness. So let me increase the opacity. And we can see that the mountains in this model are even higher than in the flat model without refraction. Let me just show you. So this is with refraction, and I'll also show without refraction. And you can see that the mountains pop up a bit lower than with refraction. And that's actually to be expected, because the facts that light bends towards a denser medium and that the atmosphere is denser at lower altitudes are independent of the shape of the Earth. So we get some looming even in the flat model, and that basically only makes it worse. So far it looks like the globe is winning, but let's give flat Earth another chance and look at Bev's photo. Once again, let's look at how the models fit without refraction first. And small note here, I rotated the photo half a degree to the right, so that it lines up with the simulations better. It just looks like Bev, or his son, who apparently took the photo, didn't hold the camera perfectly horizontally but tilted it slightly. Anyway, it's not actually very important, I'm just mentioning it for the sake of completeness. So let's check the globe model. I will increase the opacity, and we can see that once again without refraction the mountains are lower in the simulations than in reality, and if we take a look at the flat model we again see that they are much higher than in reality. So let's check the models with refraction again. I'm using the standard refraction here too, even though in the photo we can clearly see a mirage. That is likely caused by a non-standard temperature gradient near the water, and I could probably reproduce that with some guesswork and trial and error, but above the mirage the gradient is likely close to standard, so we should get good results with this approximation anyway. And as far as I know, the photo was taken fairly recently, so I assumed a higher temperature than for the Kevin Jackson simulation, 283 Kelvin, so about 10 degrees Celsius. So let's see how that worked. And again, we see an almost perfect fit. The buildings and mountains fit very well, so let's take a closer look at the turbines again. Let me zoom in here. And it turns out that they can actually be seen much clearer in this photo. Actually, when it's zoomed in like that, it's a bit less clear, but you can clearly see the bright stripes here, and exactly in the places predicted by the model. We can actually see the turbines even clearer if we bump the contrast a bit. So here is a version of the photo with decreased brightness and increased contrast, and we can clearly see that the turbines are here. Let's again compare that with the simulation, and we see that they are exactly in the places that were predicted. But to be precise, we should note that the lineup isn't perfect. If we zoom in a bit, we can see that the hill in the simulation, the hill on which the turbines are in the simulation, is a bit higher than in the photo. And this is likely due to non-standard conditions in the atmosphere, but it's also interesting in this case because it means that the drop in reality is actually greater than the globe model with standard refraction predicts. And again, the time has come for the flat Earth model with refraction, so let's check this out. And again, we can see that it's just even worse than the flat model without refraction. Again, let's compare. This is the flat Earth model with refraction, and without, the mountains appear slightly lower. So yeah, again, refraction has made it even worse, and we can see that nothing really lines up. If we line up the tower and ice blast, then for example the turbines are in completely different places. They are predicted here, but they in reality are visible here. Let me decrease the opacity again. Yep. So basically, once again, the globe model prevails. And that's it. We've checked both popular photos of Blackpool taken from Southport, and we see that the globe with refraction is the best fit for both of them. Flat Earth doesn't seem to fit at all. So scientific standards of reasoning dictate that we should discard all the models except the globe with refraction. One final bonus: I've heard that there are plans of going to Southport and photographing the view there from a drone, so I prepared 2 more simulations in advance. GIFs showing what it would look like to change the observer's altitude between 9 and 309 meters, both on a globe and on a flat Earth. So here is the one on a globe, and the one on a flat Earth is this one. I'll let it go through to the end. I'll actually post the links in the description of the video so that you can just go there and see them for yourself, or download them if you want to. Oh, one thing worth noting here probably is this purple line in roughly the middle of the image. It's the so-called eye level, so the horizontal direction. So you can see that it rises as the altitude rises, and it was the same in the globe model. Except here it never drops past a certain point, and because of the drop, because basically the Blackpool Tower and the whole of Blackpool is so distant that it already dropped a bit, so the eye level is never below the base of the tower. And here we can see that when the altitude drops to 9 meters, then the eye level is basically below the base. Yep, like that. And to better compare the 2 simulations, here they are side by side, but with decreased size, so that they actually fit together. And you can see that there is a significant difference in what they would look like. So if someone actually goes there with a drone and films it from such altitudes, we'll be able to make a time lapse and compare the result with the simulations to gain more evidence which model actually fits reality better. Finally, I emphasize once again that the simulator I've used is publicly available, and every part of it, source code and config files included. Links will be in the description of the video. I encourage everyone watching to give it a shot, play with the values, see how they affect the end result, and basically that I haven't been cheating here. Everything is out in the open for everyone interested in checking it. And that will be all for today. See you in the next video. Bye!